Okay, so we had a quick history about leading up to the discovery of the MS and how it was implemented back in the day. And we talked about a couple of guys that were kind of leading this initiative and led us into the concept of isotopes, which then led us into the nuclear chemistry field, which led into the discovery of the atomic bomb. And all of that was really mass spectrometer driven. But we're not going to use it to make atomic bombs. Okay, I hate to break that news to you. We're going to use it for other reasons in our laboratory that we have found it more useful than the atomic bomb. So let's talk about the MS. Now, if you've not picked up by it by now, MS is the abbreviation that I use for mass spectroscopy. And we have to question, well, what does it do, right? If I'm using a mass spectrometer in a laboratory, why would I use it? Well, number one, it provides information on the formula weight, or some people will call it molecular weight, of a compound. So the very first thing that I have to say is you better know how to calculate. Can you calculate the formula weight of a compound? Because if you can't do that, you're not going to be able to make it through this lecture. You're not going to understand why this instrument is doing its job and how it's doing its job. So that means if I give you something like water, can you say, oh, it's broken down into H and O, and there's two hydrogens and there's one oxygen. So each hydrogen from the table is 1.01, and each oxygen from the table rounded off is about 16, and I add those two together and I get 18.02. If you cannot do that by hand using a periodic table, then you're going to have an issue, and you better learn it quick, because this is going to be used over and over and over in the mass spectroscopy world. Okay, so there's the number one point. Number two, it also provides information, of course, on isotopes. So again, these are fat little atoms, and we can have anorexic little atoms too. We can have atoms that don't weigh enough or weigh too much. And what we're seeing on the table are the averages. Why is this important? Well, this would be something useful for like carbon dating. We'll talk about that a little bit later. But isotope information can be analyzed using a mass spectrometer. Number three, what particles contribute to the weight? Well, this is going to be proton, and it's going to be neutron. So you've got to go into that with that understanding. That's going to play a key role a little bit later on. Number four, what particles contribute to isotopes? Well, remember, it can't be proton number that changes the atom. The electrons do not change weight if we lose them or gain them because they're so insignificant. So this is only the neutron number. That's it. Number five, we have to remember that the periodic table are averages. Those masses are averages that are showing up on that chart. And the MS can come in many different forms. It can be standalone, but we said this is not really found anymore. This is really just for pure compounds, and it does us no good if we've got a sample that has a mixture of stuff in it. So our MSs now are paired. And we're going to see things like GCMS, gas chromatography mass spectroscopy. We're going to see HPLC-MS, high-performance liquid chromatography, mass spectroscopy. We're going to find things like ICP-MS, inductively coupled plasma, mass spectroscopy. They are rarely standalone. And now we're getting to a point where we will see these MS-MS combo systems. The machine sends it to the first mass spectrometer, and then that will send it to another mass spectrometer. That's what we call tandem. Tandem. A tandem GC-MS-MS instrument. These things are pretty expensive. The GCMS systems typically cost about 150 grand a piece, plus, depending on the model and the bells and whistles. The HPLCs are typically a little bit more, and that's because of a piece that's an addition to it. And that extra piece is going to cost about another 50 grand. So an HPLC MS system is about $200,000. The ICP MS system, these can easily run $250,000 or more. We do not have an ICP MS system currently at this time. We have an ICP, but not an ICP MS. And we have HPLC, but at this particular point in time, we do not have an HPLC MS. They're just too expensive. It's a lot of money, and we can still accomplish what we need to accomplish in the program if we just have one version of a mass spectrometer, and that is our GC system itself. Okay? So here's a slide that I like to show people. And what it does is it just kind of sums up all this information that we've learned so far. So over here to the left-hand side, you're seeing a faucet, and that faucet just basically drips out some water. And here is our H2O molecule, right? And you have been trained all along in a chemistry course or a science course to simply do just the formula weight of water. Take 1.01 times 2 plus 16 gives you 18.02. You've never questioned it. You probably have never wondered where those numbers came from. You just kind of accepted it with a grain of salt and away you went. What I like about this, though, is that it kind of tells you the breakdown. So here's the atom. So this could be maybe an atom of hydrogen or an atom of oxygen, not molecules. These are atoms, right? And the atoms are broken up into the nucleus, and the nucleus is in the center. So here's the atom itself, and then in the center, hopefully you learned in Chemistry 151, we have a nucleus, and that nucleus houses the protons and the neutrons. So both of those are going to be located in the center core of the atom. If you want to think about it, our solar system, that would be the sun. That's in the center, right? The electrons would be the planets that go around that sun, or the center, or the core. So the electrons are all basically scattered throughout the atom. We know that they're not just anywhere they want to be. We know that they've got to be in orbits and they've got to be in specific paths, just like our planets in the solar system. What I like about this, though, is that it tells you the actual masses and the charge that's used for each one. Generally speaking, in a chemistry class, they tell you protons have a mass of 1 and a positive charge. Neutrons have a mass of 1 and a positive or no charge. Electrons don't have a mass and they have a negative charge. They lie. They all lie all the way down. Fake news, people, right? All right, so masses of a proton, it's actually assigned a number. It's not 1. 1 is atomic mass unit. They did that to make a number that's easy to remember. A proton actually has a mass. 1.6 times 10 to the negative 24th grams. It does have a charge. It's a positive charge. But it's positive 1.6 times 10 to the negative 19th coulombs. Neutrons are the same way. Neutrons have the same mass, 1.6 times 10 to the negative 24th, but they have no charge. Electrons, they have a mass. It's not 0. It's smaller than the proton and neutron in comparison, but it's not 0. This is 0.91 times 10 to the negative 27th. That's a super small number. There's 26 zeros in front of that. And then the charge is a negative 1.6 times 10 to the negative 19th. So it is negative. But again, they do that as an easy way to put things in perspective. Now down here at the bottom, this is them kind of ratioing everything out. So proton is a 1 AMU, not 1.6 times 10 to the negative 24th. That's like a conversion factor. Neutron is 1 AMU. Again, not 1.6 times 10 to the negative 24th. They converted it on you. Atomic mass unit, AMU. And the electron in comparison is 1 over 1840. It's like 0.0005 or something silly like that. So they just say 0 because it's pretty close. All right, so hopefully you're walking away with some tidbits of information that you did not get in a general chemistry class. Again, they like to lie. They like to make it simple, though. That's why they did it that way back in the day. And now simple is not going to cut it. Simple is not going to help us understand how this machine works and how it does its job. So we've got to look at these details, and we've got to pick these things apart little by little by little. Now, hopefully you've been paying attention, because what you have noticed is that I have placed a focus on mass. It's called mass spectroscopy. I should put focus on mass, right? So the MS instrument, what kind of data is it going to give us? Well, I've talked about formula weights. I've talked about molecular weights. I've talked about actual gram sizes of protons, electrons, and neutrons. So the MS can give us structural features. Don't get me wrong. And this would kind of be in the world of qualitative. What functional groups are present? How is the structure oriented? How is it connected with each other? We can get that information from MS. But more importantly, what we get from MS? Mass. Hopefully that makes sense. A mass spectrometer gives you mass. Can't be harder than that. Now, specifically, what it's giving you knowledge of is the formula weight or molecular weight, however you want to call it, doesn't really matter to me, of a compound. But not just a compound. I'm also going to put on here fragments. We'll talk about those fragments in just a second, but they're going to be compounds or fragments. But no matter what they are, it's going to give me mass of these pieces. Now, before MS, before the mass spectrometer, how did people get this information? Well, they got it kind of difficult measurement ways in the wet laboratory techniques. Okay? So it was determined maybe by elemental analysis. Vapor density was another test that they would do. Freezing point depression. It really just depended on what type of sample that they had, what were the attributes to that sample, what could they do and not do in order in the laboratory to get this information. All of this would lead them to the discovery of a molecular weight or a formula weight. But the problem is that these tests take a lot of sample, it takes a lot of time, and it takes a lot of training. The MS system needs small amounts of sample. We're talking microliters here. That's all it needs in order to do its job effectively. So this is a good thing. Very small sample size. The problem is that it's destructive. You know, the UV is not destructive. When you put your sample in the cuvette and read it, you can actually take your sample back out of the machine and save it for another test. The infrared is not destructive. If you put your sample in an infrared in some type of specialty container in order to get the analysis on it, it's not going to destroy your compound. You could actually take that and you could reuse it. The AA, that's destructive. It took your sample and it burned it into a flame and it got rid of it. There was no way to get that sample back. The MS is the same as AA. It is destructive, and that could be a drawback to people, especially if they have limited amounts of sample to work with. Now, up here at the top, I said this MS could do formula weight or molecular weight of compounds or fragments. I'm also going to put on here or isotopes. It's not really the compound because it's a fat little compound or a skinny little compound. And it's not really a fragment because an isotope is the whole thing. It's just gained a little bit of extra poundage or lost some poundage. So I'm going to add a third one onto that list. Okay, so what I'll do is I'll stop at this point in the video. We'll pick back up. We'll continue on with our discussion of MS a little bit later. And we'll take a closer look at the atom itself and the makeup and what is getting ready to happen to it once it goes into the instrument to do its job.